Greetings, my name is Alexander. I'm CEO of Sandbox Geometry, and I will be speaking about a parametric geometry treatment of two central force acceleration fields. Uniform acceleration and Galileo are first space-time square. There are two acceleration fields we live with, G-field Earth and the solar G-field. Let G-field Earth be SNT1 and SNT2 be period orbits of our planet group. My presentation is in two parts. Part 1 explores SNT1, Galileo's discovery of uniform acceleration. Part 2 explores SNT2 event curves and their development by Sir Isaac Newton and Johann Kepler. I will be speaking about tools, a curve space division assembly, my choice of weapons to explore mechanical energy of central force curve space, energy corrals. I use Euclidean shapes as a containment, a place to hold mechanical energy of natural curve space to prevent energy leaks into space or back to F. Unit space and time tiling of Galileo, integer squares to build our first Euclidean spacetime frame, a mechanical map of Earth's uniform acceleration field built with the spacetime tiles of Galileo. Two fields, Galileo's M1, uniform acceleration, and Sir Isaac Newton's M2, period curves. I captured their happenings with two parametric curves, one independent and one dependent. Now I can build two central force spacetime squares, SNT1 and SNT2. Galileo's SNT1 has two diagonals, a linear freefall vector and a surface acceleration curve of M1. Sir Isaac Newton's SNT2 is structured with a curved time diagonal. 2 points on the time diagonal mark period limits, big and small orbit curves of M2. I also require a curve space directrix to limit G-field range, bringing mechanical order to M1 accretion phenomena, where to hang the average energy curve of M2. And lastly, a compound SNT1 uniform acceleration vector U and its partial, Galileo's first second free fall vector U1 fall from J to surface acceleration curve of F. A space-time square requires a specific unit meter of energy on its range side to provide predictable space-time happenings when connected with central force domain experience in a Euclidean space-time frame. Galileo's SNT1 operates with 1 second as range and domain experience at 16 feet. Sir Isaac's SNT2 works when the independent descriptor is solar. SNT2 is not a first-second freefall experience, but a time-expanded period over 2 space-time curve connecting orbit energy limits R f of r, changing M2 event curves into M2 period motion curves. In this CSDA construction, SNT1 is a uniform acceleration space-time square for Earth, with a range of 1 second and a domain experience of 16 feet. SNT2 is orbit parameters of Mars with a range of period over 2 in seconds. How long to orbit from aphelion to perihelion on the period time curve. And the domain of period over 2 in kilometers, meter of space from the most remote part of the orbit to the closest approach to the sun. Galileo's SNT1, uniform acceleration, interruption 1. Using an inclined plane and loop string interruption and roll as beats for time, he slowed falling. I begin with Galileo's first interruption sourced from time curve A, Earth's acceleration curve, surface acceleration curve of Earth. Source primitive of our first space-time square 1A, 16 feet 1 second as we know it today. Space-time square 1A sets the dimensions of our Euclidean space-time frame. I reference this tile as the first second tile. Interruption 2, his next beat metered 3 more units of roll space sourced from time curve B. At 2 seconds, series B tiles of time curve B wrap 3 more first second tiles around space-time square 1A, squaring time curve A, converting a curve space experience into a square space map of uniform acceleration tiling. He wondered, 3 plus 1 is 4. Could this be interruption 2 squared? Interruption 3. Time curve C. 3 seconds, series C tiles of time curve C wrap 5 more first second tiles around the time curve B squared, which is 2 squared is 4 plus 5 more tiles, 9 tiles, 3 seconds squared. Voila. 3 seconds squared fields 9 first second tiles in a Euclidean time frame number 3. So here's the leap, a continuing series sum of odd numbered tiles. Series A is 1 tile, B is 3 more, C is 5 tiles and D 7 tiles. Our time relative enabling events squared to determine the number of first-second tiles required to fill a Euclidean space-time frame. Take time curve D, series D tiles. Wrap 7 more first-second tiles around time curve C, 3 seconds squared, giving 7 plus 9 units of time curve D, 4 seconds squared, for 16 first-second tiles and the 4-second Euclidean time frame. Using table 1, distance to surface curve, square of second number 4 times the first second experience is 16 feet. Tags vertex J of a Euclidean time frame with data. 4 seconds ETA and 256 removed from surface acceleration curve of F. That's distance and time from surface acceleration. How about terminal velocity? Given a square has 4 sides, one side being space and one side being time, that the 2 remaining sides represent reclamation energy tangents. Abscissa and ordinate energy tangents represent required surrender of space and time needed to reach the surface curve terminal velocity. Add reclamation tangents, shaping accumulating square space, and use as coefficients to the first second fall experience for event velocity. Take time curve D. At 4 seconds, series D tiles, we have 8 reclamation tangents. This will be 4 on the abscissa side and 4 on the ordinate side. Terminal velocity, second number 4, table 2, has 8 tangents times the first second experience of 16 feet, provides 128 feet per second. Galileo did not have calculus. Note table 2, 2 times the event number as coefficient to the first second tile is the first derivative of event number squared times the first second tile in table 1. I use energy tangents for Euclidean SNT1 and calculus for his SNT1 tensor map. SNT coordinate system is no longer a set of points, domain or range, but has become a map of unit spacetime tiles having internal domain expression 16 feet in range of 1 second. Let tensor B be the energy expended to reach J. It starts from F with 0 slope, and tensor B1 is reclamation energy of freefall, falls from vertex J with 0 slope. Galileo's vertex tile J data field reads first second, 1 second squared times the first second tile is 16 feet above the surface. 2 times the first second tile per second is 32 feet per second terminal velocity. Repeat performance for C and C1. The curves of tensor C and C1 can only fit their collective head and tail at the most remote tile vertex of N2 squared, vertex K, of a Euclidean spacetime frame, and carries a data field. 2 squared times the first second tile puts us at 64 feet above the surface, and 4 times the first second tile per second is 64 feet per second terminal velocity. Sir Isaac Newton's SNT2 constructing conserved angular momentum and motive mechanical energy corral shaping period curves of M2. M2 motive energy constructions are sourced from my 2014 JMM Baltimore meet with Wolfram 2014 Tech Conference. I utilized parametric geometry corral to pen, and by pen I mean a place to gather and collect mechanical energy needed to shape event curves of M2 into period curves. I reference 2 types of orbit curves for M2. Let Sir Isaac Newton's displacement radius R be event curves and central force position vectors RF of R be period curves. I'll define available energy for M1 and M2 motion. And then I'm going to construct a SNT1 Keplerian energy corrals. We'll build an SNT2 for planet Mars using a basic CSDA. We'll construct position vectors to period limits, construct energy tangent and tangent normal. I'll use the energy tangents to cut the field spin axis and Thales diameter theorem to construct F of R period curves from Sir Isaac Newton's orbit event radii R. Before exploring mechanical orbit curves of SNT2 Mars, I want to find the available energy to sustain period motion. Since an M1, M2 energy exchange determines orbital momentum, we need 2 equal energy curves to quantify shared energy. Somewhere on the period time curve, there will be a motive curve of the same shape as potential. Enter the lattice rectum average orbit diameter. Reference level of gravity field energy curves. It is here and only here on the average diameter of an orbit can 2 unity curves coexist. Prove the shape of the average motive curve equals the shape of the potential curve. Construct the range of potential as a tangent limit to orbit space. That's the curve space directrix. Construct the shape of the potential curve. Curvature equals 1 about center F. That's a given. Compute and construct the shape of the motive curve at E tangent slope M equal -1 using focal property differential and Sir Isaac Newton's universal law. Focal property differential. Position vector is 2 units. Potential is 1 unit. 2 minus 1 is 1 unit mechanical energy. Radius of the motive curve using Sir Isaac's universal law. Position vector was 2 units. Invert for curvature. Square it. Multiply it times the constant of proportionality as the lattice rectum chord. And this is a curvature term. You need to invert it and it will return 1 unit mechanical energy. CSDA, constant of proportionality. I've taken the liberty to take the gravitational constant G, M1 and M2. These guys are not going to change much in my lifetime, and I've rolled them into a constant K, a constant of proportionality, which fits very comfortably on the lattice rectum chord. K times the curvature squared, invert this term, and it will return CSDA event radii. E tangent event slope, M equals -1 is an average diameter timestamp of central force field happening where curve space and square space shaped energy distribution is congruent. All motive energy corrals are captured between the curve space directrix and the system potential of M1. Constructing Keplerian mechanical energy corrals for the orbit of Mars. Data field from the 1983 CRC Handbook of Chemistry and Physics. Well, we needed to convert square space kilometric parameters, the green column, describing the orbit of Mars, to unity ratios of a CSDA reference frame, the orange column. To do so, use a direct ratio comparative. Place event energy curves as numerator. All right, these are the limits of the orbit, perihelion and aphelion. Take the limits and everything in between them and put them up here on the numerator. This is the average curve, the average radius of the orbit, and this is the average energy of the system. So you set that as denominator, multiply the ratio by 2, and you will have CSDA parameters. Next, I mark high-end, low-end orbit elements of Mars onto the period time curve of F and reflecting abscissa parts to the curve space directrix. Low-end parameters, high-end parameters, I take the abscissa part and put them up here on the curve space directrix. Let A be the separation boundary between micro-infinity realm of curvature and the macro-infinity domain of radius of curvature. What I'm saying in here, everything within the independent curve is the population of curvature. This is where curvature resides. Everything outside this boundary is radius of curvature. Let HE be the high-end event energy and LE the low-end event energy. Connect the position vector small a to point A on the curve space directrix. Closed ME corral between F and A with a negative slope 1 energy tangent of M2 average orbit curve 2, 0. Connect the position vector H1 to point HE. Close the ME corral between F and HE by constructing a segment connecting high energy event HE with the average orbit radius 2, 0. Connect the position vector L1 to the low energy event LE. Close the ME corral between F and LE by constructing a segment connecting the low energy event LE with the average orbit radius 2, 0. All ME corrals have the same base, 2 units, and altitude, 1 unit. Each corral has 1 unit ME representing conserved mechanical energy of an orbit. Kepler's empirical law number 2, an orbit sweeps out equal area per unit time in space. SNT2, planet Mars, we have a positive curve space directrix as operating range, operating accretion domain, the curve space lattice rectum chord. Spin diameter, period curves, and remote and near F of R orbit event limits. Construct the position vectors to period energy limits. In the interest of time, I'm going to do high-end parameters. Slope for position vectors of central force is always F of R over the event radius. High-end position vector y minus F of R will be equal to F of R over the event radius. We're going to multiply this term times X minus the event radius. Solve for Y. Convert square space into curved space, and you will have a parametric description of an event position vector. Thales theorem, E tangent normal, high-end F of R provide the period curves of M2. What we're going to do is take a position vector event, construct the energy tangent at that event, which will be a negative slope energy tangent, and then we'll construct tangent normative positive slope tangent. and we'll project the tangents into central force field space, cutting the spin axis in such a way as to provide the period curve as the diameter of r f of r, which happens to be the position vector radius. This point is Sir Isaac Newton's event radius. How are we going to do this? First derivative of the dependent curve is t over minus 2p. Y minus f of r will be equal to the t is the event radius minus 2p. P is 1 unit. We're going to multiply the derivative times x minus the event radius, solve for y, convert square space to curve space, and you have a negative slope energy tangent. The tangent normal, y minus f of r. We got to do some work on that derivative. Event radius stays the same. Got to change the sign in the denominator. Minus 2 becomes 2, positive 2. Invert the derivative because we're looking for a normal. Multiply times the derivative times the x minus the event radius, solve for y, convert square space into curve space, and we will have a positive slope energy tangent. Construct motive curves of Mars. Dependent curve vertex radius of curvature will be 2 units minus f of r. Every parabola vertex radius of curvature is 2p. 2 minus f of r will give us a 1.8218 position vector. 2 minus negative f of r, low end parameters, will give us 2.1957 position vector. Let's work with the high end position vector. We notice the magnitude is 1.8218. We also notice the potential is 1 unit. So the motive curve radius is going to be 1.8218 minus 1 will give us 0.8218 units. High motive energy curve 0.8218 cosine t plus the event radius 0.8218 sine t plus f of r. Radius of the motive curve using Sir Isaac Newton's universal law of gravity. Event radius 1.8131. Square it. Multiply it times the curve space constant of proportionality, which is the position, the lattice spectrum chord of the system. Now this is a curvature term. You have to invert it, and it will return 0.8218 shaping radius of motive energy. Constructing the high energy insulator tangent separating opposing forces of attraction and escape. First thing you're going to notice about an insulator tangent is that it's always normal with the position vector. To find a parametric description of this tangent, we need to find the abscissa and ordinate the contact point between the opposing energies of the field. Here is this side's motion, this side's potential. To do that, we're going to use the right triangle proportional. The first reference hypotenuse will be that of potential 1 unit. Second reference hypotenuse, the position vector. Compute the abscissa. First proportional hypotenuse, 1 unit of potential. Second proportional, the unknown, x. We're looking for an abscissa. Third proportional, position vector. Fourth proportional, Sir Isaac Newton's event radius. Solve for x, you got our abscissa. The ordinate, first proportional, event hypotenuse, the potential hypotenuse, 1 unit. Second proportional is y. For the ordinate, we're looking for an unknown. The third proportional will be the position vector, and the fourth proportional is f of r of Sir Isaac Newton's event radius. Solve for y, you got an ordinate. We can do a point slope. Y minus the ordinate will be equal to, we got to do some work on this position vector slope. Every slope term is f of r over r. So we're going to change it to minus f of r over the event radius stays the same. And invert the term, we're looking for a normal. X minus the abscissa. Solve for y, convert square space to curve space, and you will have a parametric description of an event insulator tangent. Convergence point of motion energy. Convergence point B, intercept of energy tangent on the insulator tangent on the curve space direction implies equal energy distribution. Motive energy of M2 is sourced from fixed field potential is not equal. This is a zero-sum distribution property. As such, curve space motive energy distribution geometry is equal once and only once, happening on the average energy diameter. Motive energy corrals change shape to accommodate conserved angular momentum experienced by event radii of Sir Isaac Newton. That completes my presentation.